So, today we will be discussing how to find eigenvalues in vectors. What you should know is how to calculate determinants, and you should also know how to solve linear systems of equations, at least for the 2 by 2 case. So today we will be only discussing the 2 by 2 case. So, quick recap of what eigenvectors and eigenvalues are. So, an eigenvector is a vector that just gets scaled by a linear transformation. So the scalar is called the eigenvalue. So here is something that illustrates it. So we have this transformation applied to v1 and v2, and this is just the same thing as this lambda, this eigenvalue times this vector. So this is what you get out of it. It's the same thing. And we can write it down with the identity, like here, lambda times the identity times v1, v2 is the same thing, because the identity times every matrix or every vector is exactly the same thing. So we usually write it down like this. This is the same thing, so these are all equal, it's just an illustration. So what we really get is we get this transformation equals lambda identity v. So we could also not write this identity in here, but it has some really good use case, because if we write it down like this, we can basically subtract this thing here from this thing and get something that looks like this. So we have AV minus lambda IV equals the zero vector, just by rearranging the terms here. We just subtract this thing from this thing here. And now, because these are both are matrices of the same size, we can subtract them and pull V out. So we have this thing here. A minus lambda identity, V equals the zero vector. Looks like this. Well, we just have the lambda subtracted from the diagonal. So, and if we solve this system, we can find two things. We can find the eigenvalues here, and we can find the eigenvectors. The first thing we do is we find the eigenvalues. And if you think about it, we know that for any transformation, to transform a vector into the zero vector, any vector, it must have a determinant of 0. So this thing here implies that this here has a determinant of 0. So accept if this is the 0 vector, but we're not interested in the case where this is the 0 vector. So the determinant must equal 0. Yeah, otherwise it cannot transform some eigenvectors v into the 0 vector 0. Yeah. So finding eigenvalues here comes down to finding the determinant that equals 0. Let's go through an easy example. So we have this transformation here, A, it has values here, 1, 1, 0, 2, and we can illustrate this. We already talked about how we can illustrate vectors and how we can plot them. And we know the first vector here, the red one here, is I hat transformed. So this is I hat transformed. And the other one here, this is 1, 2, 1, 2. This is J hat transformed by A. So it looks like this. We see this vector actually doesn't move I. So we already know that I hat has to be one of the eigenvectors with a corresponding eigenvalue of 1. This is really easy. Then the second one is a little bit trickier. We see this one here, and we know that somehow vectors from here get pushed to this side. So this one gets pushed to this side, but if it's here, a little bit above this, it actually gets scaled up like this. So there must be some vector in here that is actually just scaled. And this is the eigenvector of the transformation. It's another eigenvector of the transformation, and I just So it's going from here to here, something like this. This is just a visual understanding. It's not how we actually find eigenvectors, obviously, but it's nice to think about that. It's just vectors that get scaled. So we know that A minus this lambda I has to, like the determinant of this transformation, A minus lambda I, has to equal 0. And if you think about it, it makes sense. A transforms it into something, and if you reverse the transformation, then it has to be at 0. So we just say here I minus lambda, 2 minus lambda, and these stay the same. And now you should know how to calculate the determinant of this matrix. It's just this thing here times this thing here minus this thing times this thing. So I minus lambda times 2 minus lambda minus 1 over 0, what is 0, and this should equal 0. So this is easy because we can also already see that this is in an easy form where we can see, well, if we set lambda 1, then this thing is 0, so lambda 1 is 1. If we have 2 minus 2 here, then it also equals 0, so lambda 2 equals 2 is also a solution. If we cannot factorize it easily like that, we just have to apply the quadratic formula to find it, and you should know from high school how to do that. And then, after we found our eigenvalues here, we want to find our eigenvectors, and for that we have to know how to do Gaussian elimination and how to solve linear systems of equations. So the first thing we will try to solve is for lambda 1 equals 1. So remember this formula? We have this thing here now, and we're searching for the vector v, the corresponding eigenvector. So what we do is we say A minus lambda 1 identity, v equals 0. So we have this thing here, and we are setting up the augmented matrix, and then we have 1 minus 1, 2 minus 1, 1, 0. So it looks like this. And just by calculating what that is, it's just 1, 0, 1, 0, 2. So we see these are just multiples of each other. And now what we can do, we just subtract the first row 2 times from the second row. And then we get this thing here. And what it tells us is that 0 times v1 plus 1 times v2 equals 0. So v2 has to equal 0. That's everything that it says. And v1 can have every value. So what we get here is v1 is 3. And we have v1 times, well, it can have any value, so times itself. And v2 has to equal 0. So this is one eigenvector we can find, and we are lucky, and we found v1. The other one is also quite easy to solve, so we do the same thing. We just plug in our eigenvalues here. We just calculate what that is. We see, well, the second row already 0, 0. And here we have minus 1, 1. And this must equal 0. So we say minus 1 times v1 plus v2 v2 equals 0. So we can also write it down like that. Minus v1 plus v2 equals 0. And we see, well, v1 must equal v2. So they just have to scale at the same rate. So 1, 1 is one solution. And if we want to put it to unit length, we can do that. We know how to calculate the length of a vector, so we just divide it by square root of 2. And then if you think about it, this is just, you take the dot product of this, and you have 1 over 2 here, 1 over 2 here. And you add them, then it's 1, and the square root of 1 is 1. So we found the eigenvalues and the vectors of this transformation, of this example transformation. Eigenvalue of the first one is 1, and the corresponding eigenvector is this thing. And this is the eigenvalue of the second eigenvector, which is this eigenvector. And that's it for that.